Welcome to qnawire.
This is problem number 61 of the Stewart Calculus 8th edition, section 2.8. Part A. Sketch the graph of the function f of x is equal to x times the absolute value of x. Well, one approach we could do is to rewrite our function as a piecewise, which is a common approach when dealing with an absolute value function or a function that's related to an absolute value function. We know that the absolute value function is x for x is greater than 0 and negative x when x is less than 0. Therefore, if this is what we take and we separate this into x is greater than or equal to 0 and x is less than 0, then the function can be rewritten as x times x or x squared when x is greater than or equal to 0 and x times negative x or negative x squared when x is less than 0. Now, this should help with graphing our function here, because what we have is we have a upward facing parabola x squared for x is greater than or equal to 0. So this is the general shape we'll have. And instead of having the other half of the parabola in the positive direction, when x is less than 0, we have a negative downward facing parabola. So we'll have a parabola reflected across the x-axis. Just like that. Okay, so this is our graph for the function f of x, which is x times the absolute value of x. Part B, well, for what values of x is f differentiable? So that was part A. Part B, we look at the graph and we see that it's a pretty smooth function. We don't see any corners, kinks, or cusps. We also don't see any opportunity for a vertical tangent line, meaning that um, there are there don't seem to be any non-differentiabilities associated with those. The last one to check is continuity. Well, it's always continuous. So we suspect that this is fully differentiable. But for one check, just to make sure, we suspect maybe at the origin there may be a non-differentiability. So what we need to do is we need to evaluate f prime of a um, or f prime of 0. We're going to check two different ways. We're going to check the limit as x approaches 0 from the right, meaning that we're using this function, x squared, minus the function evaluated at x squared, or at 0, so 0 squared over x minus 0. This is equal to x, and as x approaches 0, this approaches 0. So that limit is 0, and then we also have to do the limit as x approaches 0 from the left, meaning that we choose the other function, negative x squared. We have negative x squared minus the other function evaluated at 0 divided by x minus 0. And we end up, this limit is equal to negative x evaluated at 0, which ends up being 0. So our limit from the left and from the right agree with each other. These are the limits associated with the definition of the derivative. So essentially the derivatives are the same from the left and the right, which means that it is differentiable at the origin. So we've checked every single possible non-differentiability, but we can conclude that f is differentiable for x belonging to all real numbers. So x is differentiable everywhere. Finally, part C is what is the formula for f prime? Well, what we're going to do is we essentially do the same procedure here, and we want to find this f prime of x, but we have to do it for two cases, one for this region, x is greater than 0, and one for this region, x is less than 0. So we're going to do h approaches 0 of this function evaluated at h minus the function itself divided by h. This gives us the limit as h approaches 0 of x squared plus 2xh h squared minus x squared over h. The x squareds cancel. One h cancels in each term. And as h approaches 0, this term goes to 0, meaning that our derivative, or our f prime of x, for this first region is 2x. If we repeat the procedure for the other function, we have the limit as h approaches 0 of negative x squared, where we're evaluating negative x squared at x plus h, minus negative x squared. So we'll have the limit as h approaches 0 of negative x squared minus 2xh minus h squared plus x squared divided by h. And then here, negative x squared and positive x squared cancel. One h cancels with each of the other terms in the numerator. And since h approaches 0, this h term approaches 0, meaning that our derivative is negative 2x in the region for x is less than 0. So we conclude the derivative function can be written as a piecewise function. It is 2x when x is greater than 0. It is negative 2x when x is less than 0. And we've already confirmed that the derivative is 0 at x equals 0. So we can include that bit of information either here or here, including x equals 0 in the domain of the derivative function. And so this is exactly a formula for f prime. And another way that we can actually write this, since we have 2x in the positive region and negative 2x in the negative region, another way we can write this is 2 times the absolute value of x. So this is the formula for the derivative f prime.